Okay, so what we want to talk about today is the different ways that we can add some of the different coupling reactions that we can use to add groups directly to the benzene ring. And these can save us a lot of steps and a lot of time because, for instance, I'll give you an example here that we already kind of know how to do. If I wanted to add this this alkene group to the ring, right now the way I would have to do it is I would actually have to think about adding the entire the 3-carbon chain, free radically brominating it, and then doing an E2 reaction to form the double bond. So that would be that would be 4 steps, 5 steps, because I can't add a propyl group, a straight chain propyl group to the benzene ring. Instead, what I have to do is I have to add the acid chloride and reduce that down to the straight chain to alkane. So I'd have to, in order to make this molecule, I'd have to go through 1, 2, 3, 4, 5 steps. Or no, 4 steps. And you might say, do we have to know the reagents on how to do each one of those steps? Yeah. Sadly, yes. So this is the kind of problem I could ask you next week, where I'd say, okay, give me the reagents that would be necessary in order to make that molecule. And so it's just an individual problem. A set of 4 individual problems. But we'll come back to that. So if I didn't want to do those 6 steps, and let's say I knew about the lithium cuprate reagents, I could simplify this all down into a couple less steps by saying, okay, I'm going to take my vinylic bromide, because the bromine's attached to the double bond, and I'm going to treat that with lithium metal to form the basically lithium carbanion, which is the equivalent of a Grignard. And then I'm going to add copper iodide to that to make then I'd have 2 of those along with my lithium cuprate. And then I would simply add 2 bromobenzenes, and the lithium cuprate would couple to the benzene, and I would end up adding my double bonded group directly to the ring. So I'm going to couple this group with this, and so I can do that in a couple of less steps. So the whole idea here is that if we have these kinds of coupling reactions where I can take 2 groups and one of them is a benzene ring and couple them together, I don't have to play around with all the side chain reactions that we learned about, a couple weeks ago, or quite honestly that we've learned about the entire year, because this reaction would be an E2 reaction that's no different than what we learned last semester. Okay, so that's what we're going to do, is kind of look at different coupling reactions that would allow us to take benzene and add some complicated alkyl group to it in one step. We just have to be able to make it. So that there's Heck, we're going to talk about Suzuki and Heck coupling and a couple of others. So that's kind of setting the stage for what we're going to talk about. And this, I think, is the last part of chapter 21 in the Top Hat book. They talk about some of these reactions, maybe not all of them. So let's start with this. I want to make benzaldehyde. Benzaldehyde is an important reagent for flavorings and fragrances, and so I want to make it from benzene in one step. You might suggest, let's do that by Friedel-Crafts alkylation or acylation by using this acid chloride along with aluminum trichloride. Now, I think earlier in the week we tried to do this, or was suggested that maybe we could do this in order to add a carboxylic acid group directly to the ring. And I said no, and I'm going to say no again. The reason is that forming this carboxylic acid chloride of formaldehyde, this is not a stable molecule. So I can't just go to the shelf and find this, nor can I make it except very quickly and have it immediately react. So we can't use either one of these reactions. So what do people do if they want to make sort of benzaldehyde on an industrial preparation? What they do is they are going to make this molecule immediately and have it react with the benzene. So here's the reagents that they use. They use carbon monoxide, HCl, aluminum trichloride, and copper 1 chloride. So if you mix all of those reagents together, what you'll end up forming is this species kind of in what we would call in situ, meaning in the reaction flask, and then that would immediately react with aluminum trichloride to make that aselenium ion. And the difference here is that I'm putting all of these reagents together to make this so that as soon as I make it, it immediately reacts with the aluminum trichloride and the benzene ring. So this is what's called Gatterman Coke. Formulation. And the formal, in this case, it means coming from formaldehyde. So Gatterman, I believe, was, I think the organic lab book that I have of Gatterman's is early 1900s, is in the pre-1910s. So this is late 1800s, early 1900s chemistry that Gatterman and Koch put together. But again, it's the ability to make benzaldehyde from benzene directly. And it's probably, with carbon monoxide, it's probably done on an industrial sized basis, but it is a good way that we can make benzaldehyde directly. Because right now we don't necessarily have that method, although there's a way around it. Okay, so that's one. So that's one of the first reactions that you can do to add a group directly to the benzene ring. Now, a lot of the other ones are going to be coupling reactions. So we've talked about the Gilman reagent, basically Gilman or lithium cuprate. So we take an alkyl halide, we react it with lithium, then copper, and then couple it together. That reaction has some advantages, but not necessarily a whole lot of them. So there's another coupling called Heck coupling. And in Heck coupling, what we're going to do is we're again going to take an alkyl halide, or an aryl halide. We're going to take bromobenzene, maybe chlorobenzene, and we're going to couple that with an alkene. And so I'm going to add the alkene directly to the benzene ring. And this requires us to use a transition metal catalyst. So what we actually use here is we use palladium, and then the OAC is the deprotonated acetic acid. So we've got a palladium 2+ ion with 2 acetates as our counter ions. And then the typical reagents that we use are what are called triphenylphosphine. So we've got 3 benzene rings attached to a phosphorus, which can be abbreviated as pH for phenyl 3-phosphine. So this is triphenylphosphine. The triphenylphosphine has a lone pair on it. And so that set of catalysts with the palladium and the triphenylphosphine will cause the benzene ring to couple to the double bond. And the way the double bond will couple is it will couple with this carbon, the least substituted carbon, then coupling to the benzene ring, so that what I end up doing is adding then the double bond that way. And this can be done not only with benzene rings, but it can also be done with any alkyl halide. So for instance, if I had a double bond here with a halogen and I reacted it with that same alkene using the palladium acetate triphenylphosphine combination, what I would end up doing is I'm going to end up coupling the alkyl group that's attached to the halogen to the double bond there, so I would end up actually forming a conjugated diene that way. So this molecule came from the group that was attached to the alkyl halide, and then this group came from the other group that was coupled to it. So in our case, we're really looking at the benzene ring being able to couple through this Heck coupling. So the example that I gave you earlier of wanting to make this molecule, if I had this, if I had already made that molecule, or actually if I made that molecule already, then I could do it in one step with a Heck coupling. That and bromobenzene. So I wouldn't even have to go through the couple of steps that I did with a Gilman. So that's what we can do with Heck coupling. What's its advantage? The advantage of Heck coupling is that it uses as a solvent H2O. And so anytime we can use water as a solvent, that's going to be more environmentally friendly. It's going to be more cost efficient. This palladium acetate catalyst is most likely a solid that all I would have to do is at the end of the reaction filter it out, maybe wash it off, and I could reuse it. Not an infinite number of times, but I could use it more than once. And so the idea here is now we're starting to get to more environmentally friendly reactions. And so Heck coupling is something that a synthetic chemist who's making a drug might use because they can use water as a solvent. And also the molecule over here might be a little more complicated than just a double bond with an R group on it. And to put this in context, if you're trying to make a significant drug that's got some size to it, like maybe it's a ring of 10 or 15 carbons with all the side groups on it, you're not making both parts. A lot of times one group is making this part and another group is making this part, or one graduate student might be making this and another set of graduate students might be making the other part. So the idea of these coupling reactions is everybody does their own part, and then at the end we just take the transition metal catalyst and boom, we bring them together. So, and then if you want to change one part, you make that other part and then you couple it again so that you can make a whole library of these different molecules and test them against, cells or whatever you're testing them against. So the Heck coupling is probably the most modern of reactions that we're going to see. I mean, people do SN1s and SN2s, but these transition metals are something that you don't get a really good sense of how often they're used. And they're used a ton. And something like palladium, you wouldn't have to worry about it being in the drug and causing any side effects. If we're talking mercury, you have to test your drug and make sure there's no mercury in it so that you're not taking a drug that's going to cause you neurological damage later on. So this is Heck coupling. Alkyl halide, double bond, palladium acetate. Then there's another coupling called Suzuki coupling. Now I'm not sure if Heck or Suzuki have won Nobel Prizes. Suzuki, I would put a higher rate on him winning a Nobel Prize than Heck. But Suzuki coupling is slightly different. But it's something that we've actually done before. So here's what I'm going to do. I'm going to take an alkyl halide, and I want to couple that alkyl group to the alkyl group of what's called a boronic acid. So all I need is the catalyst for this, which turns out to be actually pretty simple, palladium, and use palladium and hydroxide. And you're going to couple those two alkyl groups together to make your final product. So you can imagine that one of those is going to be, since we're talking about benzene rings, one of those should be bromobenzene. And so if we can make boronic acids in different reactions, then we can add those groups to the bromobenzene, and we can basically add the group directly onto the benzene ring. The advantage here again is H2O is my solvent, so it's environmentally friendly. And it just involves something like palladium. So palladium metal, probably not chunks of palladium metal, but probably palladium metal that has been absorbed onto a carbon surface like a carbon charcoal pellet that's covered in palladium metal, because it's the surface that's important, not the bulk internal part of the palladium. So if we can just spread the surface onto something cheap, we're good to go. Okay, so what's the boronic acid? Where does it come from? And that, the boronic acid, or I will also broaden this out and say that sometimes people use what's called a boronic ester. This we're going to treat kind of like this. Remember our BH3 from hydroboration oxidation? We would add the hydrogen to one side of the double bond and the boron to the other side of the double bond. Well, now what I'm going to do is I'm going to do basically the same thing. Only I'm not going to use BH3. I'm going to use an H attached to a boron with two OR groups on it. So this is going to be my reagent. So let me ask a very straightforward question here. I'm going to take methyl cyclohexene and I'm going to add to this HBOR2. Question number 1. How does the H and the boron add to the double bond? Does it add cis 100%, trans 100%, or 50-50? Oh, we have the cards, don't we? Does everybody have a card? If you don't have a card, come up and grab a card. If you didn't bring your card. Okay, the reason we have the cards is because they're infinitely cheap. So these cards are called, just so you know, they're called plickers. P-L-I-C. I think the name's on it. So they're plicker cards. Exactly. It's a clickerless clicker system. And it's dirt cheap. All you need is a free app from the phone. And I don't think that app is going anywhere. Like, sometimes people come up with these great systems and they fail to monetize them with their companies, and then they go out of business, and then I'm screwed because I can't use their system anymore. Not just me, but other people. So here's what happens. So you have that card. I don't have any more cards, I don't think. Okay. So I'll get you one on. Okay. Because they're on my cart, and the elevator on this side of the building never breaks down, except today. So I had everything on my cart, and it's now over somewhere else, probably being pillaged by students. So here's what happens with the cards. There are 4 sides to that figure, and there's an A, a B, a C, and a D. So what you can do is you can hold the card up, and whatever the top letter is, that's your answer. And then what I do is I take my card, or I take my phone, and I go like this, and it tallies up the results. So it's dirt cheap, and National Science Foundation and some other places have put funding into this, because if you're in a school system that can't afford clickers, everybody's got a phone and everybody's got paper to print these out. So I know when they had the We the People program, when I showed somebody this, and they're like, "Oh, can I have those? Because we go down to the Cleveland schools and they don't have clickers, and so we could ask them questions and they could do it, and it would be dirt cheap, meaning free." And then I think Dr. Butler coveted my set, so I just said, here, take it, because I have a photocopier. I could make more. Okay, question. That's behind the scenes of Flickrs. So, here's my question. Where is... Oh, we were talking cis and trans. So, A, 100% cis. B, 100% trans. C, 50-50. Okay. So how is the H and the Br going to add to the double bond? Or sorry, not the H and the Br, the H and the boron. Looking back at how did the H and the BH2 add when we added BH3? Okay. So what's your answer? You got to hold up the cards. And just so you know, if you're looking around trying to see if people are holding theirs sideways or otherwise, I think it's all randomized so that you can't figure out. But you do have to hold it like somewhat parallel to me. I do have to have some line of sight, but you don't have to, stretch out. Okay. They just changed their software, so I've got plus 4 guests. Right, I got 36 total, which is everybody. Let's see what I... All right, they changed the software. Okay, I got 18 A's, 7 B, I'm assuming, 18 A's, 7 B's, and 6 C's. So the most popular answer was cis. So we do add the hydrogen and the boron cis because remember, hydroboration oxidation adds the H and the OH 100% cis. So that boron gets replaced by H2O2 when we talked about alkanes or alkenes. Okay? So it's 100% cis. My next question then, oh good, I gotta figure out how to clear this off and ask the question again. Next question, where's the H gonna go, A or B? Or C 50-50? So where's the H gonna go, A or B or C 50-50? This is also a great way if you're like in an organization and you want people to vote anonymously or you don't want to count hands. This, as long as you have 40 people or 63 people or less, each one can get a card and you can vote electronically that way too. Oh, we have a tie nearly. We have 15 A's and 18 B's. So that means we should take a minute, discuss, and revote. So near 50-50 split between H adds to A or H adds to B. So I'll give you a minute. Where does H add? It's not very certain, is it?
I remember something.
That'd be helpful. Okay, we ready to revote? After your discussion, where does the H add? To carbon A or carbon B? Oh, and you're there. And if you're worried, it doesn't. The new version apparently doesn't tell me how people voted. It just gives me a check mark that it's tallied it. All right, we move to 23 A's and 11 B's. BH3H2O2 is what? Markovnikov or anti-Markovnikov? Anti. So that means the hydrogen has to add to the carbon with the least amount of hydrogens. So that means the hydrogen's going to end up adding to carbon A. So here's what's going to happen. The hydrogen's going to add to carbon A, and then the boron with the two OR groups is going to add to carbon B, but they are going to add cis. So whether that last 5 minutes has been successful or not, I'm trying to relate it back to what we hopefully already know. So this is the first step in that reaction. And now what I'm going to do is let's say I had this molecule and I said, okay, let's go ahead and react that with bromobenzene using palladium and NaOH. So I'm going to do a Suzuki coupling. What's going to happen? The benzene ring is going to replace in exactly the same position the boron part. So my final product of the reaction would have the top carbon looking like this, and then the benzene ring being attached there. So the Suzuki coupling takes this idea of coupling one step further, because now I have a stereochemistry and I also have a regiochemistry that I can control. By adding the HBOR2 group to a double bond, I can control exactly where the boron goes, and that's the group that I'm going to then couple in. So I just have to think about this first step and then couple the benzene ring after that. Okay. So Suzuki coupling gives me like a little bit higher level control here over my coupling reaction. Okay, so that's Suzuki coupling, and you can do Suzuki coupling. You could take a triple bond if you wanted to. Let's say I started with a triple bond here. I'm going to add that H and the BOR2 group, anti-Markovnikov, right? So I'm going to end up adding the H and the boron cis anti-Markovnikov, so that I could take the triple bond and I could make this molecule. And then whatever my alkyl halide is, and I'll just keep it as a benzene ring. I'll take bromobenzene. I'll now do Suzuki coupling on these two using palladium an NaOH, and now I'm going to basically replace the boron group with the benzene ring. So I'm able to make that molecule So again, all I'm doing in Suzuki coupling is replacing my boron group after the addition of the HBOR2 groups to a double or a triple bond. I'm replacing the boron group with a benzene ring. And I could replace it with other groups as well, but our focus right now is on benzene and making substituted benzenes. So the whole idea here of the Suzuki coupling and Heck coupling and all of that is simply, I now can put really complicated alkyl groups on the ring directly without having to put a straight chained alkyl group on there and play all sorts of games by doing all the reactions that we've learned the entire course of this year. Free radically brominating it, maybe eliminating to form a double bond, then doing some sort of Markovnikov addition, maybe make a Grignard. I don't have to worry about that. If I just prepare that alkyl group, I can just couple it in one step. And that's a much more modern way of looking at synthesis than what we have. But again, we're not going to get to the point of making, or going through like 20 steps. Even in lab, you saw the difficulty in 4-step synthesis, right? You started with tons of material, and by the end, you were having to get authentic from the bottle. If you're a graduate student and you're doing synthesis, depending on your seniority, if you're like a senior graduate student, you have lower graduate students making the stuff along the way because they're learning. And so you're constantly what's called bringing up material. You're constantly like making more B or making more C or making more D because you need that in order to keep going on. And that's not even the purity, because I think what we'll see, well, at least in my lab and Dr. Simmons' lab, because I'm going to spend the weekend taking NMRs, of those compounds is that when you get to C, when you get to compound C, you're going to see a little bit of A and a little bit of B left in there. So not even about the yield, but also you'd have to constantly purify this stuff as it moves up the chain. So, and that's the reason why we're learning all these reactions. They're okay by themselves, but what we really would like to do down the road is put them together to make new molecules. It's just we never get to that really in this class. All right, so that's Suzuki coupling. All right, next. Those are the two coupling reactions. Next reactions are kind of strange reactions of benzene rings. Reactions of phenol. Here's the first reaction of a phenol that is actually pretty, well, this one we've seen before. So reactions of phenols, we know how to put an OH group on the ring. We will know how to put an OH group on the ring by next week. We have to put an NO2 group, reduce it to NH2, make a diazonium salt out of it, add H3O+. Those 4 steps put an OH group on the ring. What if I want to make this OH into an ester? How do I do it? Aisha?
We use rid of the hydrogen in the benzene and then react that as nucleophile with carboxylic acid chloride.
I actually don't need to get rid of the hydrogen, but carboxylic acid chloride. That is one way to do it. So you can react an alcohol and an acid chloride. So ROH plus an acid chloride, a carboxylic acid chloride, will make an ester. And that's one of the more efficient ways of doing it. Where did the acid chloride come from? I forget. Apparently I'm not the only one. Here's a hint. I'm going to react SOCl2 with something to make an acid chloride. A carboxylic acid. So the carboxylic acid chloride comes from reacting the carboxylic acid with SOCl2 to make the acid chloride. We talked about that when we talked about Friedel-Crafts acylation. But I can react the alcohol directly with the carboxylic acid to make the ester as well. What do I need? Who was in lab yesterday afternoon?
Source of H plus.
Isn't that what we attempted to do yesterday in lab? Isn't that what we attempted to do yesterday morning in lab? Tuesday morning in lab? Tuesday afternoon in lab? Yes, that's what we tried to do. Remember you got a bottle in lab? It was like 4 months ago. This is more like 4 weeks ago. Right? What did you add to that? We poured that bottle into a round bottom, then you added an acid like sulfuric acid, then you refluxed it. What were we doing? Making an ester. This has a name. I know I'm going through the brick wall here that exists between lab and lecture. But this is what we did this week. So you could react, if you want to convert a phenol to an ester, you need to use either an acid chloride in the phenol, or you could react the carboxylic acid H plus and do Fischer esterification. So if I asked you next Friday and said, here's benzene ring, how do you go from benzene ring to there? Okay. You could do it. Nitro, to reduce to aniline, to diazonium, H3O plus to phenol, carboxylic acid and H plus. 5 steps. So we can do that. Let's see. Bless you. Might as well cover this while we're here. I can take my aniline, which is my NH2 attached to the benzene ring, and I can convert it to this amide. How do you think I could do that? No, this would be the source for making the diazonium salt. I just want to add this C double bond O R group to the nitrogen. First way is acid chloride. So an OH or an NH group will add to an acid chloride the same way, and so I'll be able to make my amide. You might say, could you add a carboxylic acid to it? No, but we'll find that out in a few weeks. Why not? I could say, how did we do this in lab 3 weeks ago? And I'll just go ahead and make that a rhetorical question, which means I'll answer it. And the way we did it in the lab, because remember we took and we put this group on the nitrogen before we KMNO4'd the CH3 group. And then we took this group off last week so that we could then add the NH2, so that we could add the carboxylic acid, the ethanol, and make the ester at the other side of the molecule. What did we do here? We actually used acetic anhydride. We used a combination of acetic anhydride, and I also believe we also used sodium acetate to do that reaction, to put the CH3 group on the nitrogen. So, and we'll talk about the acetic anhydride reaction a little bit later. So that's going to be the most efficient way to do this reaction now, for the moment. So we can convert OH groups and NH groups to their corresponding esters and amides on the benzene ring. Let's see. I'm out of time. Normally that wouldn't faze me. I would just go extra minutes, but I'm out of time. So the last thing, maybe I could make this a question to ponder for the weekend. Might as well complete this. These three. How do you convert an OH group to an OR group? How do I make a phenol into an ester? So maybe that's a question you can ponder over the weekend, and I can ask somebody at the beginning of class on Monday. Okay. All right, on Monday we're going to finish this up and talk about nucleophilic aromatic substitution, which I think is the last topic, and then we'll go from there. I think this will have most of the reactions for Monday's problem set that's due. that was in Wednesday's folder. If not, somebody send me an email and say there are problems on there we can't do, and you'll have those due on Wednesday. Yes, and I'll take your homework problems